In this chapter, we are going to give the definition of a continuous function. We either say a function is or is not continuous, and the property is called continuity of a function. So consider some nice function that looks like that. At the point A, we have some function value f of a, and continuous means that close arguments give close results. So first, we want the a to be in the domain of definition of the function. That means fa must exist. The next natural condition is that there is some neighborhood of a, of points, that also belong to the domain of definition to give some results, to compare the results. And then we say the function is continuous if we can find, if for any neighborhood of the function value, we can find some neighborhood of a such that all these points gives result in this neighborhood. So the definition goes this way. We say a function f is continuous at a point a if a is in the domain of definition and some neighborhood is in the domain of definition, and for all positive epsilon there exists at least one positive delta such that if x is close to a, that means the difference x minus a is small. How small? Not more than delta. And the points may be on the right or on the left of a, so the difference may be positive or negative, but not too large. That means we take the absolute value, and this difference should be less than delta. That means if we have here the value a plus delta, this is the value a plus delta, and this is the value a minus delta. So we want all these points, satisfying this condition, to give results in the epsilon neighborhood of fa. So this upper point is fa plus epsilon, and this lower point is fa minus epsilon. So if x is close to a, then the function values of the function at x are close to fa. Close means that the difference is small, and again it may be positive or negative, so we want the absolute value to be not more than epsilon. This is the definition. So once again, we say a function f is continuous at a point a if the point is in the domain and some neighborhood is in the domain, and for all positive epsilon, here epsilon measures the deviation, the error of the results. It's called epsilon, which is similar to the word error, the difference of the function values on the y-axis. So once again, if for all positive epsilon that measure the difference of functions values, there exists at least one positive delta that measures the difference, the deviation, the difference of x values, such that for all x satisfying this, that means close to a, that means all x values such that x minus a in absolute value is less than delta, that implies, or then, the function values are close to fa. That means f of x minus f of a in absolute value is less than epsilon. This line can be written in some different way. We can say that if x is from the delta neighborhood of a, we denoted neighborhood U, sorry, U, not wall, U. X is close to A, means X is in the delta neighborhood of A. Then this is close to this. That means the function value f of x is in the epsilon neighborhood of fa. Here the radius of the neighborhood is delta. This is on the x-axis. And here the radius of the neighborhood is epsilon. This is on the y-axis. This is the usual notation. If you write it the other way around, if you swap the two letters in everywhere, it's also a valid definition. But this is the way most often it is written this way. We can write it still in a different way. Namely, all the points from this set are mapped by the function f in a set that is a subset of the epsilon neighborhood of f of a. So a subset is denoted by U, and this is the epsilon neighborhood of f of a. This notation is maybe new for some of you, and this needs a little explanation. If we have a function, say f of x, x squared as an example, then what appears in the bracket may be either just one number or a set of numbers. That means if we have just one number, say 3, then the result is 3 squared, which is 9. On the other hand, if we have some interval, say from 1 to 2, then we can consider the map, the image of this whole interval. The interval now consists of infinitely many points, and f of this set is the set of all the results, the collection of all the results. Well, and it's easy to find that x squared maps the interval from 1 to 2 into the interval from 1 to 4. So, and this is the case. In this bracket, we don't have just one number. We have a collection of numbers. We have a neighborhood. We have an interval. We have infinitely many points. Which points? The neighborhood of A. All these points in this part. And we want all these points to be mapped by the function f into a set. This time it is this set. This set to be in the, or a subset of the epsilon neighborhood of f of a. So we have 3 equivalent ways how to write the definition of the continuous function. And in the next section, we will consider right continuous and left continuous functions.